Now we need to understand more about the motion. We need to take friction into the picture. In order to do that, we need the normal force, because it turned out that the friction force depends on the normal force. So this is a simple situation. You have an object with mass m, the weight downward is mg, the upward normal force is n, the magnitude of n is equal to the magnitude of mg, because there is no motion along this direction, acceleration is 0, therefore n minus mg is 0. Okay, so n equals to mg. Now let us change a few things. Let us add a force and play with the direction of the force and see how this will influence the normal force. If you act with a force like this force, if applied along this direction, still there may be no motion. For the vertical direction, you can decompose this force into two components, one horizontal and one vertical. The horizontal component is F cosine theta, and the vertical component is F sine theta. So now along the vertical direction, you have N and you have F sine theta up, and you have mg down, right? Since there is no motion along the vertical axis, so we still have N plus F sine theta minus mg equals 0. That is to say, N plus F sine theta equals mg, right? Okay. So now the normal force, when you solve for N, it is mg minus F sine theta. So N now is less than mg. N is less than mg. Okay. So if you use a string or a rope to pull on the object in this direction, eventually you are reducing N. You are reducing the value of N. Okay. Keep this in mind, because as I said earlier, N is important. We need it when we learn about friction. Right now, we are just setting the stage to understand how N may change or may not change. Consider this other situation. The same object, but now we are acting with a force directed downward, like this. So now, if you decompose this force into two components, horizontal and vertical, and apply a Newton's second law, so you have N upward minus mg minus F sine theta equals to 0. Therefore, for this situation, N is greater than mg. N is greater than mg. N equals mg plus F sine theta. Okay. Now we will change a few things. Imagine the same object, but now we have an elevator. The object now is accelerated upward with some acceleration a. Okay. So now when you apply Newton's second law, F equals ma, a is not 0. A has a positive value. Okay. So the net force here, N minus mg, N minus mg is equal to ma. Right? This is a Newton's second law. The net force is equal to mass by acceleration. So from this equation, we solve for N, and N now is equal to ma plus mg. Okay. So now we understand several things. We understand that n can be equal to mg if the object is on a flat surface, horizontal surface at rest. N can be greater than mg. It can be less than mg, depending whether you have an external force acting this way, n is greater than mg, or acting this way, n is less than mg, or if you have motion with some acceleration, also n is greater than mg. Okay. Let's consider also these situations. If the object is on an inclined surface like this surface, okay, n is always normal to the surface. N is perpendicular to the surface. Because of that, we call it the normal force. Normal means perpendicular. But now the weight force mg may be decomposed into two components, one parallel to the surface and one perpendicular to the surface. Okay. The one that is perpendicular to the surface is opposite to n. Okay. Since there is no motion along the y direction, then for y, we have the force for the gravity. It is minus mg cosine theta, pointing this way. If you want the net force, then you will take n into the picture. N plus this force adds to 0, so n in magnitude is equal to mg cosine theta. As for the other component parallel to the surface, it is mg sine theta. Okay. So along the y prime axis, there is no motion, so ay prime is 0. Therefore, n minus mg cosine theta is 0. Therefore, n equals mg cosine theta. Now we are ready to start talking about friction force and learn about friction. We are all familiar with this situation. If you have an object on the ground and you are connecting a string to this object or rope and trying to move it, as you apply force at the beginning, the object resists the motion. But if you keep increasing the magnitude of the force, at one point, the object will start moving. At one point, the object will start moving. At that point, this means the component of your force along the horizontal direction, this component, was greater than the force of friction. Okay? At that moment, when the force is slightly greater than the force of friction, then the object will start moving, will start sliding. So originally, the object was at rest. There is rough surface down. There is contact between the object and the surface. And if you try to move the object, there will be a resistance. The force of resistance, we call it friction. Always friction acts in the opposite direction. So you are trying to move this direction, then the friction will be squared in that direction. As you increase your force, friction will increase until at one point your force is greater than friction, so the object will start moving. Once the object starts moving, now we move from static friction to kinetic friction. So we call it Fk for kinetic friction. You will note that kinetic friction is always less than static friction. Okay? So the force that we needed to overcome the first situation at rest is greater than the force that we will need to keep the object moving. because friction during motion is less than friction at rest, than when the object was at rest. Okay? So applying what we learned in the normal force is mg minus F sine theta. The horizontal axis x, we have max equals F cosine theta minus the force of friction. And the force of friction is directly proportional with the normal force. This is an important thing to learn, to take note of. The force of friction is proportional directly with the normal force. And we change it from proportionality into equation form using proportionality constant, mu k. Mu is a Greek letter. We use it here to represent this proportionality constant, which we call it the coefficient of kinetic friction. The coefficient of kinetic friction. Okay? So now we calculate the force of friction from this formula. Usually the coefficients of kinetic frictions and static frictions will be listed in tables in standard physics books. You can get, depending on the kind of surfaces here, you can get the value for mu and multiply mu by n, so you get the frictional force. And this way you can study the motion, you can calculate AX. Okay? So here, if we substitute for n from this relationship between n, mg, and the component of the force, then we end up with this result for the motion along the x-axis. In this table, you see values for the coefficient of kinetic friction and the coefficient of static friction. You will always see that static friction is greater than kinetic friction. The coefficient for static friction is always greater than the coefficient for kinetic frictions. One of the lab experiments, you will study friction and you will be able to measure kinetic friction and static friction, and you will observe this yourself for all kinds of surfaces. So this is steel on steel, then aluminum on steel, you have these numbers. Copper on steel, less, it's 0.53 for static friction, 0.36 for kinetic friction. Rubber on concrete, this is the highest friction. It is 1. Okay? It is the highest friction. No other material will have static friction 1 except rubber on concrete. Okay, so now we understand why we use rubber for our tires, the tires in our cars, because the friction is maximum. We need this friction to move on the highways, on the streets. Okay. When motion starts, it is dropped from 1 to 0.8. Still, it is the highest on this list. The coefficient for kinetic friction between rubber and asphalt or concrete is 0.8.